So we're letting x, y, and z be random variables such that x is a standard normal and conditional on a value of x, y, and z are i.i.d normal with mean taking the value of this conditional information. And here we're going to find the joint PDF of x, y, and z. So the joint PDF of x, y, and z is, and now it's useful to basically condition on x, because if we know x, we have information about y and z, and they will be independent. So conditioning on x, y, that was the wrong variable. So conditioning on x, so basically we have y, z conditional on x. Probability of, not probability, we're doing the density obviously. Like so. So this is just rewriting by definition what we have here. So this we can do. And this, we know what it is. It's a Gaussian, and that is a conditional. So once we know this, we can do the rest. So now let's write. So I'm just going to write this as of x, and the rest is basically with now we're subtracting off x, so it's y minus x, and phi z minus x over the real space, so whatever x and y are defined, which is plus and negative infinity here. We can write out these terms if you want to see the full derivation. So that this would be equal to now, so we have, so let's do the following. We can just say that this is basically done, but we could, if we wanted to continue here, so I'm going to do that. And here y and z are conditioned on x independent, so we can write f y conditioned x, z conditioned on x. We have this term there. So now y is normal, exponential, and now this is not standard normal anymore because it depends on the values of x. So we have y minus x squared, but the variance is still 1, divided by 2. And this will be the same for z. I'm just going to copy this, remove the y, write z here, and same thing for x, except that it is standard normal, so we can just write x squared. Right. So, and yeah, just note here that these terms are what I meant by z minus x and y minus x there. Okay, so in the second part of this exercise, y and z are conditionally independent. That's what we used. We're going to discuss now intuitively whether y and z are also unconditionally independent. So one way to view this problem is to say, just using a graph, and these are basically inspired by causal graphs. So if we have, what do we have? We have x, basically a random variable, and that the value of x generates y. Well, basically this is n condition, so it's conditioned on x, like so. This is distributed, 0, 1. Same with z. This is distributed normal, also x, so it's little x, 1. So what is this graph saying? Well, it's saying that if we condition on the value of x, so once we know x, we plug in that value into y and z, and then we draw z, and then we draw y. And in this case, they will be independent. So we have no information about z from y and vice versa. And here, if we don't condition, so unconditionally, if we know the value of y, we can calculate or infer the value of z. So knowing the value of y gives us information about x. And for example, knowing the mean of y after making several draws, we can infer the value of z. So x and y here are basically unconditionally dependent. Sorry, y and z are unconditionally dependent. Okay. In the third part of the question, we asked to find the joint PDF of y and z. And here we can just leave this as an integral. We don't have to calculate what the value is. And that we do by having to sum or integrate over all values of z. So f of x and z and y, no, y and z doesn't matter. It's the same thing as summing over all, integrating over all values, so all support of x, and the joint distribution of these three variables. And so, and we know, we just calculated in A what this is, so we can just plug it in. It's exactly this term here. Copy this, move it over here, like that. And this looks like a quite complicated derivative. And in the exercise here, we're saying that this can be found if we go into complete the square and use some facts about the normal distribution. I'm leave that up to you. I'm not going to do it here, but basically the trick was to sort of move from here to there and here, and the rest is algebra.